let's introduce deterministic data flow now. In fact, there are three main paradigms of concurrent programming, and deterministic data flow is the simplest one. It really is very straightforward and simple. It supports all the techniques of functional programming, and that's what we're going to see. Just as a brief aside, what are the two other paradigms? Well, one of them is called message passing concurrency. This is used, for example, in Erlang and Scala actors. In this paradigm, concurrent activities each runs independently, and they send messages to each other like people sending letters in the real world. This is a relatively straightforward paradigm. In fact, we can combine it with data flow, and that's what we'll see at the very end. The third paradigm is called shared state concurrency. This is used in many systems, typically, for example, in object-oriented systems. They usually use this. Java monitors is a form of shared state concurrency, what they call synchronized objects. Here, the activities are in fact sharing the same data, and they try to work together without stepping on each other's toes. In fact, this is a much more complicated paradigm. That's what experience shows us, but it's unfortunately still used in many languages. But let's now talk about deterministic data flow. So let me show you this with a simple example, and starting with a simple concept of an unbound variable. It's all based on unbound variables. So let's create an unbound variable in memory, and let's try to do a calculation with it. So for example, here x is an unbound variable, y also is unbound, but then we try to do y equal x plus 1. So what happens when we try to do this? What happens when you try to use an unbound variable in a calculation? Well, from this simple question, we build the whole deterministic data flow idea. Let me take a step back and say, well, let's talk about variables in general that are not initialized. An unbound variable is not initialized. Different languages do different things with such variables. But what's the right thing to do? Well, let's see. In the language C, for example, the addition will simply continue, and the content of the variable is whatever is in memory at that point, so it's some garbage value. In Java, things are more disciplined. The addition continues, and x's value will be 0 if it's an object attribute of type integer. For example, in Prolog, execution will stop with an error. There's no way to add. We don't know x, so we don't continue. In Java, another case, the compiler will detect the error if x is a local variable in a block, that it's not been initialized. In Oz, and this is where the deterministic data flow comes in, execution will simply wait. Quite civilized, the execution will wait patiently until x is bound. And this is data flow. It is the moving of data, the data flow that drives the execution. So this is what we're going to see in this course. Let me give a final one, which is even more sophisticated, but it is used in particular cases. In constraint programming, if you do y equal x plus 1, what do? Well, you take the whole equation, y is equal to x plus 1. You add it to the set of constraints in the system, and the constraints will be solved when enough information about the different values is known. But execution will simply continue using the constraints that you know. This is a really nice way to compute, a way that we're not going to talk about in this course, but I really strongly suggest you take a look at that. It's in fact the most powerful form of declarative programming that exists. Okay, so that was an aside. Let me now show how the deterministic data flow works. So here on the left, we have declared x globally and y locally, and we do y equal x plus 1, and then we display y. Okay? So what happens? Well, this execution will stop just before the addition, and it will wait patiently forever. There's no notion of timeout. It will just wait. When can it continue? Well, if someone would bind x to an integer value, then the addition could be performed and execution will continue. But who can bind x? And here's where concurrency come in. Another concurrent activity will bind X. That's how it's done. The two concurrent activities will talk to each other. If another activity does X equal 20, then this activity here, the addition will continue. We will do 20 plus 1 and display 21. This is what is called data flow execution. So data flow execution, so here's a diagram. We have the first part here is the progress of activity A from left to right. The second part is the progress of activity B. Activity A does y equal x plus 1. And since x is unbound, activity A will wait at that point, at point 1, just before the addition. When activity B binds x equal 20 at point 2, then activity A will continue and eventually it will display 21. Now, what happens if activity B binds x equal 20 before activity A reaches point 1? Because there's no fixed speed relation between the two activities, that is definitely possible. Well, in that case, x will be bound to 20, and activity A will do y equal x plus 1, will calculate 21, the same value as before, but without waiting. So you see, in all cases, activity A will eventually see the value 20 and will eventually display 21.